Welcome everybody to the most recent Building Science Deconstructed webinar on NFPA 285 and WRBs, weather resistant barriers. My name is Peter Barrett. I am the Product and Marketing Manager with Dörken Systems. I've been with Dörken for over 14 years now, and I've been involved in the water management end of the construction business for, oh my God, over 25 years. I do work with the Air Barrier Association of America. I sit on the board of directors and on the audit committee. I'm also involved with RAINA, the Rain Screen Association in North America, and co-chair the residential committee with them. I'd like to welcome everybody, and I hope that I'm able to provide some useful information today. For those of you who don't know, Dörken's been manufacturing construction materials for over 125 years. This is our manufacturing facility in Herdecke, Germany. This is where all of our weather resistive barriers, our spunbond membranes, are made. This is the facility just up the road from there, where we are constructing brand new state-of-the-art manufacturing facilities. This is our North American plant in beautiful Beamsville, Ontario. This plant since has another addition on it as well. This is where we manufacture all of our dimple membranes, our below grade drainage and moisture protection materials. And this is our plant in Istanbul, Turkey. So without further ado, let's move on to the informational section of today's presentation. NFPA 285 explained, wall assemblies, WRBs, and code compliance. The genesis of us creating this AIA presentation was really that in dealing with both architects, general contractors, and other similar manufacturers, there was a whole lot of misunderstanding about what they could do with NFPA 285, when they had to comply, and how to comply. So we went and decided to put this together. So you do get an AIA credit if you've provided us with your AIA number on registration. If you forgot to do that, or conversely, if you would just like a certificate of completion and don't need an AIA credit, you will all receive a thank you note for attending this, and just simply reply to that, and we can send you your certificate of completion, or we can get you that AIA credit that you need. So when we thought we needed this, we reached out to the fire consultant engineers at Priest Associates, and in conjunction with them, we assembled this presentation. So today you will see information regarding the use of combustible building materials in wall assembly that increase the risk of fire in the built environment. The relationship between the weather barrier and NFPA 285 compliance is often misunderstood, hence us assembling this. The course will cover the basics of the NFPA 285 test standard and building code sections relevant to weather resistive barriers. We'll also address the basics of test wall design, including cladding, insulation, etc., how wall systems that include weather resistive barriers are analyzed for engineering evaluations, and compliance strategies. As required by the AIA, we have some learning objectives. At the end of this course, participants will understand the basics of the NFPA 285, the basics of the building code as it applies to weather resistive barriers, the basic tenets of wall design, test wall design, including claddings, insulations, and other components. You'll also understand how WRBs are analyzed for engineering evaluations and how those are used. So let's start with the basics of NFPA 285. Initially, there was a universal building code standard addressing multi-story fire tests. At the outset, it was a full-scale fire test. In other words, they built a full-scale wall, which was very expensive, and every time a component was changed, the wall had to be retested. So to help address this complexity and the expense, Jesse Beitel invented the 2/3 scale test. This eventually became the Universal Building Code test, which, when the ICC came into play, was passed over to the National Fire Protection Association, the NFPA, to manage. So the purpose of this test is to measure vertical and lateral flame spread for combustible materials to be used in non-combustible assemblies. So the building code basically allowed you, or this is the qualification for the building code, to allow you to use combustible materials in non-combustible or labeled non-combustible assemblies, so long as you pass this fire test. Now, in the 2/3 test, the height between floors is 7 feet, whereas in a real building is typically 10 feet. Hence, with some fast math, you can see that that is, in fact, the 2/3 scale test. So why does the NFPA 285 exist? Well, quite simply, people use combustible materials in large-scale buildings, and they can catch fire, and they can lead to some very tragic results. So the 2/3 scale test was developed to help prevent uncontrolled flame spread in tall buildings. Ultimately, they were developed to reduce property damage for people and property, to allow occupants time to get out of the building, so and basically provide a much safer building. There's often very flammable components. Cladding can be flammable. Fiber cement can be flammable. But this is one of the major sources of confusion. What triggers the requirement for your building to be NFPA 285 compliant? In and of itself, building height is not a trigger. It is actually considered a sub-trigger when considering WRBs in claddings. So the commonly held 40-foot rule really applies to, or really applied to whether or not you were using weather-resistive barriers. You can find other rules that would apply to HPLs, the high-pressure laminates, or the ACMs, the aluminum composite materials. You can find 40-foot rules, 50-foot rules, and 75-foot rules. We're not dealing with those today. We're going to deal with it strictly with respect to weather-resistive barriers. One thing often overlooked is the fact that the instant you use a plastic foam in the wall for building type 1 to 4 at any height, NFPA compliance is triggered. Certainly in my personal experience, that's one of the most overlooked requirements. So let's actually look at the pass-fail first. We will deal with the actual building code in a moment. These are the actual pass-fail criteria for NFPA 285. As a general statement, so long as the flames don't go higher than 10 feet or not more than 5 feet to the left or right, you can pass. There's also thermocouples in the system that will measure temperature at specific locations. A typical test may have 60 or 80 thermocouples. For example, number 11 would be outside the wall, 10 feet above the window. Number 28 may be 10 feet above the window inside the wall in the air gap. But as long as those thermocouples don't measure temperatures greater than 1,000 degrees Fahrenheit, you'll likely pass the test. However, always wait for the official lab report to ensure every thermocouple passed the test. So here's the basics of the building code. There was no requirement for NFPA 285 testing with respect to the inclusions of weather-resistive barriers in the system in the 2009 code. 2012 was the first attempt to limit WRBs and require NFPA 285 testing in buildings over 40 feet. Hence the commonly held understanding that 40 feet is the trigger for any NFPA 285 compliance. It's only a sub-trigger with respect to the use of water-resistive barriers. Most of us in the industry felt that that was a little restrictive. There's a wide variety of flammabilities in weather-resistive barriers. We'll touch on that again a little later. But in essence, that was fixed in the 2015 code. So let's have a look at the actual code itself. So here's the section from the 2015, or sorry, from the 2012 code. If you're keeping score, it's 1403.5 of the International Building Code. This is the part that basically said in types 1 to 4 that are higher than 40 feet above grade plane and contain a combustible water resistive barrier shall be tested in accordance with and comply with the acceptance criteria of NFPA 285. Well, since all water resistive barriers are flammable to one degree or another, that suddenly meant that you had to test all wall systems. And that's why the industry claimed that it was too restrictive. This was changed in 2015, where in essence it said, if the WRB is covered by brick, concrete, stone, terracotta, stucco, steel, per some specific thicknesses, it's acceptable. But also, if exception 1 is not met, the WRB is allowed only if it has low flammability and no other combustible components are used in the wall. And in those red circles, you can see some of the very specific measurements for the water resistor barrier. It must have a peak heat release of less than 150 kilowatts per meter squared, total heat release of less than 20 megajoules per meter squared, and an effective heat of combustion less than 18 megajoules per kilogram, in accordance with ASTM 1354. 2018 has exactly the same language. There was no change in the 2018 language, and there's also no change to the 2021 IBC language. So let's look at the way a typical wall is assembled. So the basics of the test wall is a lot of components. I'm not going to read through every single one of these because I have 2 pages of them. Here's a typical wall components. As it says, it can include but are not limited to. What I want you to get out of this isn't so much exactly what each of these components are. We will touch on them a little more later on. But what I want you to get out of this right now is the idea that there are many, many possible combinations in the wall. You can do some fast math and probably figure there's over 10,000 possible combination. And any one of these components are available in multiple brand. There's many layers in the wall. The reality of this is that it's impossible to cover every possible type of wall design in a single fire test. One can figure at the very least, there are 2 to 4 fire tests required to qualify as many options as possible. But there are manufacturers out there that have done as many as 18 or more fire tests to qualify as many options as possible. So let's try to break the wall down into a couple regions. This will help us look at the components a little more simply. Let's look first at region 1, which would be the base region of the wall. Different parts of the base region of the wall and how you analyze them for testing are very important. So typically the base wall would be built with gypsum board on the inside, let's say steel studs, and gypsum board on the outside. There's usually a fire stop at the floor line usually an air gap if the insulation doesn't fill the entire stud. That's the space between the steel studs. And there are a whole bunch of different options for insulation: fiberglass, mineral wool, spray foam. Again, you can already see how the possibilities are multiplying. Generally, to keep things simple, you want to use 5/8 gypsum on the interior. That's usually what's needed to run a fire test. Half-inch type C gypsum will probably generally crack and allow fire in and lead to failure. A steel stud wall is often done because then through engineering evaluations, it's possible to allow CMU or concrete base walls because steel stud would be considered a worst case scenario. We'll touch a little more on worst case scenarios as we move along. So that's the base wall, region 1. The complexities multiply as we look at the exterior of the wall. Let's call this region 2 with many of the exterior components. So now you can see how the permutations are starting to add up. So we've added other components to the base wall that ended at the gypsum sheathing. It is possible, by the way, to design with no exterior gypsum sheathing using foam directly over steel studs. Weather barrier outboard of the sheathing, often continuous insulation, and other weather barriers, possibly outside that, an air gap in cladding, are the primary components of region 2. Now, again, if you look at the numerous brands in these combinations, you will end up with a huge amount of possibilities for combinations and the possibility to test. Luckily for many of us in the weather-resistive barrier business, many of the insulation manufacturers have tested a large amount of walls with WRBs either behind the foam or the insulation or in front of the insulation. And pardon me, as we touched on earlier, engineering evaluations can allow either the tested one or less flammable ones without having to do a full-scale test. Here's some examples of typical base walls. You can include concrete masonry units or a stud wall with interior 5/8 type X insulation wall board, galvanized steel studs spaced at 24 inches on center with lateral bracing, installed every 4 foot vertically or as required. You can test a stud wall that will allow concrete masonry units or concrete walls and deeper or heavier studs at 16-inch on center. Going a smaller distance between the studs make the walls more stiff and adds more thermal mass. If you add a thicker gauge, you'll have more metal, also making more thermal mass. Thermal mass can make things burn better. Let's look at some typical cavity insulations. Really, we're just showing here different kinds of insulations that can be used. You can see fiberglass, mineral wool, paper or foil faced fiberglass or mineral wool, bearing in mind that glue is used in the facer and glue can add to the flammability, or insulation binders could also burn. Mineral wool with no binders does not burn. So you can see some non-combustible insulations there. Combustible insulations would include, let's say, spray foam or cellulose insulation. Though I personally have never seen an NFPA 285 compliant system that contains cellulose insulation. Typical exterior sheathing would be a minimum 1/2 inch unrated or 5/8 fire resistant rated exterior type gypsum sheathing. As I said earlier, you can have none, but this will allow the insulation to be exposed to fire on both sides. There are a lot of different weather resistive barriers on the market. There are fluid applied, obviously. There are mechanically attached, there are self-adhering. All of these will burn differently. All of these will contribute to the fire differently. So, oh, did I go the right way? I did. So if you have no insulation with the WRB applied directly over the sheathing, then that can be flammable. You will find that there are minimums and maximums, or sorry, there's only maximums right now applied to the insulation market, but there is a proposal that's in the draft form to add minimums as well, because as I said, if there's no insulation, the WRB can burn more, and the insulation can act as a protective layer. It's important to realize too, with insulation manufacturers, that they all have different chemistries. So just as an example, if you test with one polyisocyanurate brand, that does not mean that all polyisocyanurate brands are approved in that assembly. That test is very specific to that polyiso that you have tested with. Again, that's because many of them or they all have different chemistries. They will all burn differently. As I just hinted at, there is a new standard being worked on that will require a minimum foam thickness, as well as there's already a requirement for maximum foam thickness. But that draft is probably years away from becoming effective. Let's have a quick look at the air gap. The air gap is an important part of any rain screen assembly. This is the part that provides the ventilation for drying. This is the part that provides the space for drainage. However, when you're doing a fire test, that same air gap can also provide more oxygen for the material to burn. So typically, they will say a maximum air gap. The new standard that I mentioned, they're going to agree to allow the air gap to be plus or minus a ½ inch, so that will give everyone a little more flexibility. But nonetheless, the air gap is also an important listing that you'll see in any NFPA document. It's important not to exceed that, because that will change the burning characteristics of the wall. Claddings. There are many claddings out there, not all of which at the moment are covered by NFPA 285. So if you test with brick, for example, that can get you the ability to use other heavy masonry claddings. If you test with ACM, you can probably get sheet metal or fiber cement allowed as well. You can also allow masonry claddings if you test with ACM. If you test with brick, the report will say you can use other masonry systems with closed joints. If you test with ACM with a semi-open joint, then you will probably be allowed open joint materials for other materials like sheet metal or fiber cement. So if you want to use brick with open joint, for example, and you passed ACM, you will be allowed. So all of this means that you need to look at what you've passed and use the joint system and with the cladding that you've had tested. So let's look at window perimeters. This again is an often overlooked detail. If you select a particular insulation and wall system, you need to ensure that you follow the specific details for that wall system in the fire stops. A great example of this one is the third one on your screen, the XPS window head. It's important to note in that particular one, for example, that the fire stop above the window, that little sort of orangish gray piece, is mineral wool. And that is designed to help keep the flame from reaching the plastic foam. Often when you see plastic foam designed into a system that is trying to be NFPA 285 compliant, these are the details that are overlooked. But typically, the polyiso industry runs their test with aluminum flashing around the window, which quickly melts during the test, which means so long as everything else passes, they have few other restrictions around the window. The EPS or XPS, expanded polystyrene or extruded polystyrene, typically tests with that third detail you see there, mineral wool or fire-treated lumber, to help keep the fire from burning through. Important to realize, whatever you test with in this detail, you are stuck with that or something better. You must use that or something less flammable. The most recent version of the NFPA 285 standard, the 2019 revision, also has a seam in the cladding above the window and recommends to test with aluminum of 0.04 inches thick flashing for the window perimeter as a worst case scenario. But it also says you may test with whatever the manufacturer recommends. In absence of other instructions, the lab will likely use aluminum. Flashings around windows is another important question we get. Flashing around the window is not a trigger for NFPA 285. It is not covered by that at all. So whatever you use doesn't affect your compliance. So here's a slightly better look at that number 3 detail that I was talking about. And the important point here is, in order to ensure that the designed wall assembly is compliant, as a design professional, you should request the full report in order to ensure that your design contains these details. Without these details that were done on the tested wall, your building will not be compliant. So let's have a quick look at how WRBs are analyzed for engineering evaluations. You've heard me mention worst case testing several times. You've probably been waiting for me to explain it, so I shall. So the principle of worst case testing is really looking at the thousands of possible assemblies, realizing that testing is very expensive, in excess of $25,000 US, realizing that the average test lab can do maybe 1 or 2 of these a week, and then deciding what you should test. Your fire engineer will generally recommend testing the worst case possible. What does that mean? That means you want to test the most flammable assembly you can that you think will pass. Something that will just get you over the line, because that means everything less severe can be made acceptable through engineering judgments. So, for example, if you run a test with a highly flammable weather barrier underneath the insulation and a moderately flammable weather barrier in front of the continuous insulation and behind an ACM and pass the test, that means if you replace any of the weather resistive barriers with less combustible ones than the original, then it becomes an improved design, a less flammable design, and a compliant design. Important to realize that as you do the layer by layer analysis of your system, that changing the components will affect the results. Adding a component will affect the results. Removing a component will affect the results. A fire engineer will not write an engineering judgment unless he has analyzed the entire assembly. What weather-resistive barrier is being used? What is its location? And then through references or data provided by clients, he can prove whether or not the proposed design meets the requirement. In some cases, more testing must be performed to prove that the weather barrier is less combustible than the one in the approval. Once that is done, you can get a compliant system. So how do we analyze these weather-resistive barriers? Well, as I said earlier, the tested WRB is used as the baseline. So whatever you used in the primary big burn or big wall assembly, that's used as the baseline. And water-resistive barriers that are less flammable than the tested WRB can be allowed to replace it. So how do you determine what is less flammable? Well, that is what I alluded to earlier when I was talking about the code changes. ASTM E1354, commonly known as the cone calorimeter test. And you analyze that and compare the data to the baseline, and if it's less flammable, then you can use it. What are the parameters? Well, those are very similar to the ones that we saw in the code earlier. Time to ignition, peak heat release rate, total heat release, and heat of combustion. So there might be certain exceptions, but that must be analyzed very carefully by a fire consultant. But the bottom line is all four of those items should have better numbers than the base material to which you are comparing in order for it to be approved. So an important part of this presentation, and if you leave with nothing else, you should remember, always follow NFPA 285 tables and the required details. I truly mean that if you get nothing else out of what I've said today, that's the most important component. These tables lay out exactly what you may use in each specific layer and in combination with what other components from other layers. Each table is unique. The components of this are derived from the big burn testings that we talked about, doing the full NFPA 285 tests. You can only use the components listed in the table. You can't go from one manufacturer's table to another and say, hey, it's okay here, it must be okay in that one. Because as I said, if you change or alter a component and the system has not been tested and this table does not allow it, you no longer have a compliant wall system. Many specifiers will look at a manufacturer's spec sheet and try to derive it from there. It's important to realize that most architects are not fire experts. Neither are most product salespeople. I am not a fire expert. It's important to involve a licensed fire engineer to evaluate any planned wall assembly. Sometimes a specifier will hear, my product is NFPA 285 approved. So then they jump on this product and add it to their list without doing due diligence to see how it fits in to a table such as this. There is no such thing as an individual NFPA 285 product. NFPA 285 compliance comes through systems, not individual products. A component may be part of NFPA 285 compliant systems, but is not in and of itself an NFPA 285 compliant product. Only very specific combinations of materials are allowed based on how the test was done. So tables like this, any manufacturer that has products that are part of an NFPA 285 compliant system will have a product like this. Installation manufacturers, for example, may have 10, 12, 15 tables similar to this, but it's important to read each individual one. It's not a pick and play menu. You need to follow each individual table. You cannot combine a product from this table with products from another table or another manufacturer. So I'm going to dwell on this again. It's important to realize that there is no such thing as an NFPA 285 product. There are NFPA compliant systems of which a product may be part, but the product itself is not NFPA 285 approved. You cannot combine components from one table to another without proper experience and test data to support the claim. So simply because you find it mentioned somewhere in the table doesn't mean that you can use it however you want, or that a given component is mentioned in another compliant system doesn't mean that you can drag it over and drop it into yours. So spec sheets are often misunderstood. This is misused, but I prefer misunderstood. And that misunderstanding can be dangerous. Contractors sometimes replace components when availability is delayed, particularly now when we have some very dramatic supply chain issues. But again, in order to be NFPA 285 compliant, you can't simply drop it in without checking with a fire engineer. You should always follow the NFPA 285 tables. If your supplier doesn't have one of these tables, I would not recommend that you use the product if you need to be NFPA 285 compliant. So these tables are based either on the full burn or on an engineering evaluation. And that's the only way you can ensure compliance of any planned wall assembly. So now that you've designed the compliance system, it's important that all of the installation details are followed, both when you're drawing the details as well as when the building is being constructed, because those details are critical to the performance of the wall should there be a fire. You've heard me mention engineering evaluations a whole bunch of times. An engineering evaluation, an EEV, or an engineering judgment, or commonly referred to shorthand as an EJ, for many of these past years have been used and accepted, but they have not technically been allowed. There is now in the 2019 change to the NFPA 285, they are officially accepted. The new guide offers a way to do a layer by layer analysis, and it will allow any water resistive barrier only if it is behind 2 inches minimum of 4 pounds per cubic foot minimum, unfaced mineral wool that meets ASTM 136, non-combustible, and if the remainder of the wall complies with NFPA 285. In other words, if you put stuff around your WRB that doesn't burn, it's acceptable. But again, EJs or engineering evaluations need to be done by qualified fire engineers. This will allow you to use a wall, be NFPA 285 compliant, even though the full NFPA 285 burn test has not been done. An engineering judgment to date typically can run, depending on the details, maybe around 5,000 US, give or take. So in summary, we've been through the basics of the NFPA 285 test. We've seen how it's done. We've seen how you burn, and we've looked at the full list of pass-fail criteria. We looked at the basics of the building code as it relates to weather-resistive barriers right up to 2021. We've looked at the basic of test wall design, starting with region 1, the base wall, and then out to region 2, where we have the WRB, the insulation, the airspace, and the claddings. And number 4, we just finished discussing how water-resistive barriers are analyzed for engineering evaluations. So this concludes the NFPA 285 and weather-resistive barriers implications for wall design course. If you have any questions, you can email us at technical@dörken.com, and we will answer all of your questions. You can also reply to your thank you email. We will also happily answer all of your questions, or we can arrange a discussion or a meeting at your convenience. I just want to tell you, now that we've finished the AIA portion, some of the stuff that we do at Dörken. I encourage you to visit our website at www.dörken.com and go to the Delta Academy portion, where you can find a whole lot of information on building science from people like Dr. Joe Stiebrick, Dr. John Straub, Graham Finch, all of which is generic, good building science information. You can also find good branded information on our products and how to use them. For example, you can find some good installation information on our below-grade nipple membrane, Delta MS, very popular for protecting foundations. This is our most popular water-resistive barrier, Delta Vent SA, which is a vapor permeable, self-adhering water-resistive barrier. It's commonly known as a peel and stick. It's both airtight and permeable. It's a 3-layer WRB that is very easy to use. We have a full set of BIM models for you to use that allow you to quickly drag and drop into your design. Very aggressive, high performance insulation. To note, we actually manufacture all of our own WRBs. We make them at that plant I showed you earlier in Herdecke, Germany. Delta Dry and Lath is one of our newest and most popular products. It adds a rain screen and a lath all in one step, making the installation of conventional stucco and manufactured stone much easier, and includes the safety and protection of a rain screen, adding the reserve and moisture protection of both ventilation and drainage. It doesn't change your details at all. Very easy to apply, safe and quick, and very popular. I touched on Delta MS earlier. It is a nipple membrane using air gap technology that helps keep your foundations dry. It's made from 60% recycled and 40% virgin material. Doesn't require special equipment to put on. It's easy to learn, no PPE, available across Canada and the US, and fully code compliant in both jurisdictions. Thank you to everyone. I appreciate you tuning in today. My name's Peter Barrett. Thank you for coming out, and stay well, everybody.